d by dx or d by dt of t to the power n will be nothing but n t to the power n minus 1. And on the other hand, if I've got integral t power n dt, then this can be written as t to the power n plus 1 by n plus 1. So these are the only two formulas that we will be using for the calculus that is there. And as and when needed, we will look at other formulas that are there. Now, we know that there are three equations of motion. The first one being v is equal to u plus at. The second one, s is equal to ut plus half at square. And the third one, v square is equal to u square plus 2as. Now, all of these three we have derived graphically. So now let us go ahead and derive all these equations using integration and differentiation. That is the method of calculus that is there. Now let us look at the third equation. The third equation is v square is equal to u square plus 2as. Now if we see s is there, so we will have to take the velocity expression only. But we also have acceleration. So how do we arrive at this particular form? So for that, we will have to take the following differential formula. That is, acceleration is equal to dv by dt. So in calculus, we can do certain algebraic, let's say, operations. So what I'm doing is I'm multiplying and dividing by ds. So this term, that is ds by dt, now becomes velocity. So here we can see that acceleration can be written as v dv by ds. Now if you see, v dv is there. So from the formula that we had done for t last time, we can see if it is t dt, we end up getting t square by 2. Now the similar thing we can do here. So what we will do, we will take ds to the other side. So a ds is equal to v dv. Now we have to set the limits for this. So integral a ds is equal to integral v dv. And here we can take the velocity is 0 for displacement 0. And for displacement which has a particular value, the velocity becomes v. Now instead of 0, what we will do is we will take this as the initial velocity. Ideally, when there is displacement is 0, body might not have any initial velocity. But in certain cases, it is seen that even though displacement is 0, it would have been moving previously with some velocity. So certain graphs give us that feeling. So right now we can go ahead and use these as our limit. Now a and ds, there is no dependence. So I'll take acceleration outside. Integral s is equal to 0 to s is equal to s ds is equal to integral v is equal to u to v is equal to v dv. So just like how I've done it previously, again I will just put in values here so that we can understand what the integration is all about. So in red, so this is s power 0, does not affect our equation. This is v power 1. So we end up getting a times integral of s or integral of ds is nothing but s. So 0 to s is equal to, now integral of v dv is there. So I'll get it as v square by 2. So this is v square by 2 with the limit varying from u to v. So I will have a times s minus 0, upper minus lower limit, is equal to half is common. So it is going to be v square minus u square. So that would imply 2as is equal to v square minus u square, or v square is equal to u square plus 2as. And this is our third equation of motion that is there.